you all know, my name is Erik Barbosa. I'm currently now my 5th year of my PhD here at Georgia Tech. Very excited to share what I've done these past 4 years and talk about my proposal. So the title of my research is Stable Salt Hydrates for Thermochemical Energy Storage in Buildings. More technical difficulties. All right. So the motivation behind my work is related to the energy distribution within the United States. As you can see here, about a third of the energy goes towards buildings, and within that, about 50% goes towards thermal loads. So that includes space heating, water heating, and cooling. This is a very large amount of energy going towards this end use. And in order to meet sustainability goals, we need to decarbonize this large thermal load. There's very promising solutions, as you can imagine, such as renewables, including solar and wind energy. However, they don't really supply energy whenever there is a demand for heating buildings. And this intermittency is really preventing the usage of these renewable energy sources. So in order to combat that and align this mismatch of renewable energy supply and demand, we're thinking of using a thermal battery or thermal energy storage, which is basically just a thermal battery. As you can see up here, it's basically a battery where you charge it and you discharge it as you would any other battery. In order to actually make this function, of course, you charge it using renewable energy or some kind of waste heat to introduce the thermal energy. And then when you need to discharge that heat, all you have to do is use that energy for your building whenever there's a large demand of heating in your building demands. Now, there are many different types of thermal energy storage materials out there. I'm going to focus on salt hydrates, which are a type of thermochemical material. The reason why I'm focusing on this is due to its many advantages. The first such advantage is that they have a high volumetric energy density, which you can see here. It's significantly higher to other thermal energy storage materials. This high energy density translates to compactness, which is really important for building applications where space is limited. Another advantage is that they have negligible self-discharge, and this is due to the thermal energy being stored in the chemical bonds. And exactly how this functions is we're using a solid and gas reversible thermochemical reaction where we have a solid salt and a gas vapor. Now, in order to actually make this work, we first start with our hydrate salt. We heat it up. This causes the heat to be stored with an endothermic reaction where water vapor is allowed to chemically detach from the salt, and you're left with your charged dehydrated salt. To discharge this heat, all you have to do is introduce that water vapor back into the salt, and that causes the exothermic reaction where heat is produced for temperature control in your buildings. Now, as I mentioned cycling throughout this presentation, I referred to this hydration and dehydration reaction. And the actual effectiveness of this material is going to be based on the reversibility of this reaction. And the last advantage I'm going to talk about is that they are generally a low-cost and non-toxic material. Now, in order to actually use these salt hydrates, we need to have a fundamental understanding of the equilibrium behavior. This will help further progress the use of these materials. So to understand the phase transition, of course, we begin with the Gibbs free energy equation, which tells us the equilibrium conditions at which a reaction will occur. With this Gibbs free energy equation, and assuming the vapor to be an ideal gas, we can derive the Clausius-Clapeyron equation. This equation tells us the exact conditions at which we can hydrate and dehydrate the salt. And as you can see here, we have the change in enthalpy and change in entropy of the reaction, which are material thermodynamic properties. And this delta H, the change in enthalpy, that's that energy density. It's the theoretical value that I spoke about earlier. Now, using this Clausius-Clapeyron equation, we could draw up the phase diagrams. Using this phase diagrams, the colored lines there are representative of this Clausius-Clapeyron equation, which tells us the distinct phase behavior transition for each of these salts. As you can see here, for strontium bromide, we have the anhydrous states, we have the monohydrous state, and we have the hexahydrate state. And using this phase diagram, it's going to be really important to make sure we understand it and use these conditions to actually hydrate and dehydrate our material. So we have to make sure we're above that red phase transition line and underneath that deliquescence line, which I'll explain shortly what the deliquescence is exactly. These phase diagrams can be experimentally validated using a simultaneous thermal analysis, which is just basically a combined TJ-DSE, where you can measure the mass absorption and desorption and the associated heat of that reaction. Now, these salts materials, they sound pretty well known. However, after experimental, some experiments and then literature review, we noticed that there's, of course, some limitations associated with these materials. The first, these limitations are directly associated with the solid-solid transition as the salt hydrates and dehydrates. The first limitation is the hygrothermal instability. So this just means it's associated with the water vapor absorption. This limitation is caused through deliquescence. As you hydrate your salt, you may introduce too high of a driving force, and that causes your material to form a liquid solution. Additionally, if you dehydrate this at too high of a temperature, it may cause the material to melt and also form a liquid solution. In both cases, you can just continue to heat them up to dehydrate them to go back to a solid state. But however, as you can see, if you were to dehydrate that liquid solution, you're end up with an agglomerated salt particle. And this is really bad for our use. Because as I mentioned, this isn't just a heat transfer problem, this is also a mass transfer problem. And that reduced surface area to volume ratio within the agglomerates is going to introduce significant vapor diffusion resistance, which is really bad for our end case use. Another hygrothermal instability that we'll talk about is associated with the nucleation barriers of this phase transition. What ends up happening, if you have too low of a driving force, you cause the salts to nucleate at a very slow rate, and that causes the salt basically unable to fully hydrate within a useful amount of time. The exact area in which this low driving force occurs is in this metastable zone, as you can see here. And both the agglomeration and metastability, they're hygrothermal instabilities, and both of them result in very low thermal power output. So that just means that the heat is being produced at such a slow rate that it's very low thermal power. And the last limitation we'll talk about is the mechanical instability, and this is associated to the exact hydrating and dehydration behavior. As you see, the salts, when they hydrate, they'll expand, and then they dehydrate, they'll contract. And that causes mechanical instabilities where there's called pulverizing and breaking apart, as you can see here. And this change in the microstructure will cause unwanted results within your salts. Now, the primary focus on the past 4 years has been associated with coming up with approaches to stabilize these materials and making them more fully reversible. Now, aside from the actual materials, there's also plenty of limitations with the reactor design of these salt hydrates. There are many different types of reactors out there for these solid and gas reactions. However, I'm going to focus primarily on a packed bed reactor. Just a bed where you have a salt that's stagnant in there and you have the vapor that's flowing over it. It's just a simpler type of system that can be used, and yeah. So these packed bed reactors, their particle sizes that are used within them, they're usually optimized to get that optimal bed performance. However, as I mentioned with these material limitations, they cause a change in the actual microstructure or the particle sizes. When you agglomerate the salt within your packed bed reactor, you're left with basically a giant rock in there, and that, of course, as I mentioned, causes significant vapor diffusion resistance. With pulverization, as your particles get smaller and smaller, this is also pretty bad for the packed bed reactor as it causes significant pressure drop, preventing really the use of this packed bed reactor. Now, aside from the material limitations, there are also some limitations associated with the actual way that these packed bed reactors of salt hydrates are modeled. We need to make sure that we use a very robust model that captures all of the heat and mass transfer phenomena that is occurring within this reactor. So this model needs to account for several things. First, it needs to account for the interparticle transport. So that's the actual vapor transport around salt particles themselves. We need to account for the intraparticle transport, and this of course accounts for the diffusion of the water vapor within the pores of the salt microstructure. And then we also need to account for the chemical reaction, which is when the salt, or the vapor reaches the salt to actually react. Now this multi-scale approach is very necessary in order to actually produce a usable product that can be placed within your building. Now based on these limitations, 4 thesis questions arise, which I'm going to present to you today. The first thesis question is associated with the pure salt hydrate materials and how do we overcome some of their limitations. The second thesis question is how do we increase the cycling stability of these salts using salt matrix composites. The third thesis question is related to taking these salt materials and forming them into actual form factor that's going to be representative of what's going in a packed bed. So in this case, it's going to be a pellet. And the last thesis question is of course related to that multi-scale model and how exactly does pelletized salts hydrate and dehydrate within this packed bed reactor. So I'm going to focus first on question 1, which is what material level approaches can improve the hydrothermal stability, vapor diffusion, and reaction kinetics in pure salts. So to answer this question, I'm going to do 3 things. I'm going to first establish a standardized PGA-DSE characterization method. After that, I'm going to utilize a uniform particle size to mitigate the structural instability. And then I'm going to develop a binary salt mixture to mitigate the hydrothermal instabilities of the salts. So as I previously mentioned, there are nucleation barriers within these salt hydrates. So there's a very common salt, strontium chloride, and that purple shaded area is that metastable zone. And I decided to hydrate the salts within those 3 different icons there. And they're color-coded with the results here from this TGA data. As you can see on the green, where it's in the metastable zone, the green dotted line, it doesn't fully hydrate due to those nucleation barriers. In the orange dashed line, it does fully hydrate just past the metastable zone. However, it hydrates at a slower rate. And then with the solid blue line, this hydration occurs at a faster rate. And of course, this is due to the higher drying force. So again, the main outcome from this is that we need to make sure that we use the phase diagrams to dictate the conditions at which we run or cycle our salts. Another very important limitation that we noticed in literature is just due to the very different results from the same part salt samples from different literature studies. And the reason why, in this case, we have strontium bromide. The main takeaway from this slide, this part right here, is that the phase diagram should dictate the exact conditions at which we need to operate these salts. Another major limitation noticed from literature is that they can hydrate the salts in these different STA inputs, such as the gas flow rate, the sample mass, and it can result in different measured energy densities, especially when compared to theoretical energy density, which is at the enthalpy of the reactions I previously mentioned. So from these results, we decided to come up with a study in order to come up with the optimized STA input parameters to use for the rest of the experiments throughout my PhD. So exactly how I ended up doing this, I took the STA, I varied the sample mass, and I varied the purge gas flow rates. And while doing so, I was able to measure the mass uptake and then also the measured energy densities. And the measured energy densities at these different input parameters, I compared it to theoretical prediction using that equation you can see there, which gives us a % difference from the theoretical value. So the first parameter I varied was the sample mass. As you can see, I varied it from 5 milligrams to 25 milligrams. And the main takeaway here is you can see that the larger sample masses just creates a thickness layer, and that causes vapor diffusion resistance. So you need to work with the smaller sample mass. Next, I varied the purge gas flow rate, which is that gas that goes throughout the actual furnace. As you can see here, I varied it from 20 milliliters to 200 milliliters. And really that's middle, 100 milliliters per minute ended up being the optimal condition. This is primarily due to higher purge gas flow rates introducing too much noise within the actual measurements, and then too low of a gas flow rates did not produce enough of the actual convective heat and mass transfers in order to actually cause the salt to react at a fast enough rate. So making that 100 milliliters per minute the optimal condition. Now, the rest of this presentation uses those optimal STA input parameters. However, aside from using the correct conditions, we also know that these salt hydrates, they still have mechanical instabilities with them. As I previously mentioned, the salts, as you hydrate and dehydrate them, they'll cause to break apart and self-pulverize. And as you can see here, we have for strontium chloride, magnesium chloride, pristine means that it's the sample directly out of the container. Precondition means that this sample was hydrated and dehydrated up to 5 cycles. And as you can see, the microstructure is significantly altered. And as you can imagine, if you were to measure the results from these different materials, you would have different actual results from them. So we want to prevent the sample-to-sample variation. Something else we noticed from literature is that these materials, they'll keep pulverizing and breaking apart into small particles until eventually they reach a critical particle size. So what exactly that means is that as they break apart, they'll become a part where they can no longer become a smaller particle, and this prevents then the sample-to-sample variation. So in order to reach this particle size, what we ended up doing is taking our salts and we ball milled them. This is a method just to break apart materials to very fine size. So using this, we can control the cycle-induced pulverization and reach that critical size where it doesn't break apart anymore. So as I mentioned, this ball milling, it creates a small particle size and it creates it to be structurally stable as it no longer breaks apart. And here are some STA results based on those different conditions. So we have the ball milled, the solid blue, which is the small particle size. We have the pristine, which is the dashed gray, dotted gray line. Of course, this is out of the box. And then we have the precondition, which is that dashed red line. As you can see here, the small particle sizes, as you would expect, result in a higher hydration rate. And additionally, from this energy density and thermal power outputs, we see that due to strontium chloride fully hydrating in the ball milled states, it has a higher energy density. With thermal power, it also is increased due to that faster rate of reaction. Similar results can be observed with magnesium chloride. However, in this case, energy densities are very similar just because in both cases the salt fully hydrated. But the thermal power, of course, is significantly different just due to that faster rate of hydration. Based on these results, we can characterize the salts without any vapor diffusion resistance, and we can get the true material characteristics of these salts. After doing many experiments, we noticed that the salt hydrates, they can be characterized into 2 main categories. The first being like that of magnesium chloride, where they are highly hygroscopic and they will deliquesce. As you can see here, the magnesium chloride at 40% relative humidity, a low relative humidity, it starts deliquescing and forming a liquid solution where it agglomerates. The second category of salts is such as strontium chloride, where they have high nucleation barriers or metastability, so they require higher vapor pressures in order to actually hydrate them. So based on this 2 different types of salts, we came up with a hypothesis. What if we take one that is highly hygroscopic and one that is suffers from that metastability? If we were to mix them, could some kind of synergy arise from them where it produces a much more hydrothermally stable salt? So to test this hypothesis, we mixed different ratios of strontium chloride and magnesium chloride. We noticed that the 50-50 mixture really balances the hydration behavior of both salts, so we stuck with the 50-50 mixture. After hydrating this salt up to 40% relative humidity, we noticed that there isn't any deliquescing, even though magnesium chloride technically should deliquesce at these conditions. Once we hydrate it at a higher vapor pressure or higher relative humidity, we do notice some slurring here. However, after dehydrating the slurry, it does return back to actual particles, fine particles, as it was proved before. And to explain what's happening here with this hydration behavior of this mixture, I'm going to explain it here within this diagram. So as I mentioned, we have 50% strontium chloride, 50% magnesium chloride. And as we hydrate it at 25% relative humidity, the magnesium chloride does fully hydrate, whereas the strontium chloride doesn't, as you can see here. But however, the 50-50 mixture does have actually a pretty nice energy density. Again, this is more likely due to just the magnesium chloride hydrating and then some of the strontium chloride partially hydrating. At 40% relative humidity, strontium chloride should not fully hydrate due to metastabilities, whereas the magnesium chloride, it will deliquesce in these conditions. But here at this 40% relative humidity conditions, we do prevent the deliquescence, and then we have a pretty high energy density. And this is more than likely due to a synergistic effect. Magnesium chloride, as it hydrates, it's trying to deliquesce or pull excess moisture. However, that excess water vapor ends up causing localized higher vapor pressures for the strontium chloride to fully hydrate and prevent that instability. And then with the 60% relative humidity, strontium chloride does fully hydrate, the magnesium chloride deliquesces, but then the 50-50 mixture, it has a significantly higher energy density. And we attribute this to the enthalpy of the solution. Again, this magnesium chloride is forming a slurry, so that adds on to the additional solid gas vapor, solid gas enthalpy. And then we just dehydrate it once again. So based on these results, we observed that binary salt mixtures, they can overcome the hydrothermal limitations of the individual salts, and we can create a material that functions at a wider range of relative humidities. So that's the end of question 1. I'm going to move on to question 2, which is, to what extent can salt and matrix composites improve the charge and discharge cycling stability? In order to answer this question, I'm going to first characterize the effect of nanoconfinement using different salt matrix materials. I'm going to obtain the optimal salt loading that balances energy density and the hydrothermal stability, and I'm going to evaluate the cycling stability of these composites. So, as you can see here, calcium chloride is a salt that's, as I mentioned, it's very highly thermal unstable. It wants to deliquesce and form this liquid solution. And this is pretty bad because calcium chloride, it's one of the most desirable salts because it has the highest energy density of all the salts that I previously mentioned. It also is relatively cheap. So both of these characteristics will result in a pretty low levelized cost of storage. So we want to see if we can make this calcium chloride function for these building applications. So to do this, literature has demonstrated that salt matrix composites can actually stabilize these highly thermal salts. And there's many different types of salt matrix composites out there. There's different materials that you can use and different matrix structures. However, for this study, we decided to work with a mesoporous silica. You can't really see it in this SEM. However, the mesopores have been characterized in literature before. So within these clusters, you have these tiny nano-sized pores where we impregnate the salt into them. And the reason why we do that is to cause this nano-confinement effect. This nano-confinement effect, what happens is your salt, it will hydrate and it will deliquesce within these mesopores. However, due to strong capillary attraction forces within the mesopores, it causes the salt to not leave or leak out of the pores. So you're left with overall a macroscopically dry sample. And it causes it to be much more stable and prevent any of that agglomeration, as I previously mentioned. Additionally, for this study, we are working with a hierarchical silica. So this is a material that has two different pore size distributions. One being the mesopores, which is in the clusters, and the other being the macropores, which is the space between the clusters. And this macropores additionally increases the water vapor diffusion just due to the space where it can go through. So to actually create our salt matrix composite with these mesoporous silicas, we use a very simple wet impregnation technique where we take our calcium chloride, we dissolve it in methanol. After stirring that for a while, we add the mesoporous silica and allow that additionally to stir for a little while longer, and then we just dehydrate that overnight. So again, this method is pretty simple. It's easily scalable using industrial equipment to produce kilogram batches. And for the rest of this presentation, I label my composites using this nomenclature where we have our salts at the exact matrix material and then the weight percent. Now, for this study, I used two different types of silicas. The first silica I'm going to mention is the commercial silicas that we purchased from a company called Evonik. These silicas are synthesized using a sintering technique, where technically they grow these nano-sized silica particles and then they fuse them together. And the space between the fusions, the slits, end up becoming the mesopores where the salt is impregnated into. And due to this slit-like pore size or pores geometries, we end up with a very large pore size distribution. This graph here is a pore size distribution graph common in literature. The left y-axis is the pore volume at the respective pore widths, and that is the markers. And then the right y-axis is the cumulative pore volume, or the interval of that pore volume distribution. And those are the solid lines. Now, additionally, with these commercial silicas, we observed that due to the constricted mesopores, the slit-like structure, this prevents salt impregnation really reaching the inner depths of these materials. The second type of silica that I'm working with is the lab-grown silica, the HSPEG that I previously mentioned, and this is done in collaboration with Dr. Krista Walton's group here at Georgia Tech. And these are synthesized using a soft templating where you have precursor materials that help create that combined macropore and mesopore pore structure. The mesopores, the precursors are tube-shaped, so that results in the mesopores also being tube-shaped structure. And due to the precursor being a consistent size, you're left with a very narrow pore size distribution, as you can see here with the black lines. Additionally, this ordered mesopores being much more ordered in a tube-like structure, it could enable salt impregnation due to easier access of the mesopores. Now that we have our different silicas and our calcium chloride impregnated within these different types of silicas, we're now going to look at the macroscopic hydration behavior. As you can see here, I have the EV26 and EV10, the commercial silicas, and it's impregnated with 68% calcium chloride. And I use 68% calcium chloride because this is the upper limit demonstrated in the literature, and we really want to have a high energy density with these materials. And the more salt you have, the higher the energy density will be. As observed here, we still observe some deliquescing within our sample, especially within that EV10. However, with the lab-grown silica, the HSPEG, we prevent any of that deliquescing, which is really impressive. And the reason why we have this difference in macroscopic hydration behavior is due to the pore size, the pore structures. Of course, the commercial being the constricted pores, whereas the lab-grown silica is a much more ordered pore. Here's the water uptake of what these samples look like at these different relative humidities. As you can see, the EV10 and HSPEG are consistently very close to one another at a higher water uptake. We attribute this to HSPEG. It has the higher it has the higher specific surface area, so this allows I can't drink the water. Thanks. The higher specific surface area of the HS-PEG creates a stronger bonds for the water to actually form within the mesopore structure. However, with the EV10, a lot of the salt is left on the exterior and allowed to deliquesce, so that's why you have the high water uptake of the EV10 as well. Now here's the hydration energy density, or the reaction rate, or the heat of the reaction. As we observe here, the EV10, it has the highest energy density at all of these conditions, and we attribute that to the dissolution enthalpy. So again, this EV10, is deliquescing significantly, and that adds to the overall measured energy density. Now, as we can observe from this slide, the internal cylindrical mesopore structure of the HS-PEG, it's really key to handling these high salt loadings and making them stable at these wide range of relative humidities. Now, looking at the cycling stability of these composites, this is the conditions we cycle it at, 25 degrees Celsius, 60% relative humidity, and we hydrate it at 1.5 hours, followed by dehydrating for at 80 degrees Celsius for 1 hour. And we decided to cycle these for 100 at 100 cycles. As you can see here, both the EV26 and the HS-PEG, they have consistent water uptake and consistent energy densities. And this is pretty significant
primarily because no one in literature has demonstrated to stabilize calcium chloride up to 100 cycles, and actually no one else has actually demonstrated up to 100 cycles before in literature. So again, the main takeaway of this is that the static confinement effect, it creates pretty high and near constant energy density over 100 cycles. So that's the end of question 2. Now I'm going to move on to question 3. This question is, how can the performance of salt hydrates and their composites be characterized in representative form factors, such as pellets, and gas environments for packed bed reactors? In order to answer this question, I'm going to develop first a model for transports within a pellet. I'm going to fabricate a composite pellet that can minimize the structural degradation. And then I'm going to evaluate the effect of different gas environments. So this is a moist air versus just pure vapor environment. So for the model within my pellet of mass transports, I have some assumptions here. I'm assuming this would be a transient 1D model. So it's just a porous pellet that's dehydrated and being hydrated by vapor. And I can assume the transient 1D due to having a 0 to 1 thickness to diameter ratio. I'm also assuming constant properties regardless of the temperature of the hydration states. And I'm assuming symmetric boundary conditions at midplane. As you can see here with this diagram to the bottom left, I need to of course capture both the diffusion and the reaction within the salt hydrate. So for my governing equation, I have the conservation of mass equation, and exactly what I am modeling here is I am modeling the transient vapor distribution within the pores, not within the salt, so the actual pores of the pellets as it diffuses throughout the pellets and then reacts with the salts, which is at end dots. This reaction with the salt is calculated using this Arrhenius-style equation, which accounts for using a kinetic equation constant. It has something to account for its hydration extent, and then it has a factor for the driving force. Now for the boundary conditions. At the midplane, of course, I have that no flux boundary condition. And then at the top condition, I can have two different boundary conditions. I can have a constant vapor condition or concentration of vapor. This is just due to air being stagnant up there. Or I can have a convective mass transfer coefficient, convective mass transfer boundary condition if the humid air is flowing across the top of my pellet. For heat transport, I have the same boundary conditions, and the governing equations, they look very similar. Of course, it's the energy conservation equation where we have, again, a transient term and then a conduction term, and then we have that heat generation term. Again, this heat generation is calculated using the reaction of the salt hydrates. Now for the boundary conditions, I also have very similar, where the midplane we have that no flux zone, and then at the top we have either a constant temperature condition or a convective mass transfer boundary condition. And then here's some preliminary results of this model. As you can see, as we have higher and higher porosity, that hydration extent, or the rate at which this pellet is hydrating, becomes significantly faster. So lower porosity just has too much vapor diffusion resistance. Additionally, even though we can increase the overall rate of hydration, it still takes multiple hours. So as I mentioned before, these salts they're very diffusion limited. So we have to come up with other methods to improve the diffusion throughout the pellets. One such method to reduce this diffusion resistance is using a pure vapor environment. So traditionally in air, where we have air and vapor, the vapor has to also diffuse through the air to reach the reaction sites of where the salt is. So if we remove that, where in a closed system there's only vapor present, we could significantly improve the diffusion. To test that, we decided to come up with a closed system testing rig. Again, closed system meaning that it's just a pure vapor environment. And this is demonstrated here. So within this closed system testing, we have a vacuum pump that just evacuates all the air that's within this system. Once all that air has been evacuated, we can then use the water tank to produce vapor pressure at a controlled vapor pressure to go to the salt container, which will hydrate the salts in this pure vapor environments. Here's some of the preliminary results for strontium bromide as it hydrates from the monohydrate to the hexahydrate. As you can see, in the open environment, it takes up to 16 hours for this pellet to hydrate, which is significantly slow. However, for the closed system, it takes a little bit over 3 hours, which is, of course, much faster. And these results are promising to enable these pellets to just hydrate at a much faster rate. So based on these results, I have some proposed work. The first being I'm going to finalize this testing rig, and then I'm going to hydrate and dehydrate my salt silica composite pellets in both these open and closed environments, just to able to see how the will look like in a packed bed reactor. At the same time, I'm going to adjust my model that I previously demonstrated to account the cycling behavior in both gas environments, so the fusion coefficient will technically be different. Now, aside from the diffusion resistance, these pellets are also mechanically unstable. This is demonstrated here in the literature. As you can see, strontium chloride, as it hydrates, it demonstrates a 119% volumetric expansion, which causes it to crack significantly, what you can see there. So, for my salt composites, the salt in the mesoporous silica, we notice is that as the salt hydrates, it expands within the mesopores and not really expanding the overall pellet. And these results are demonstrated here for the calcium chloride in the EV26. And as you can see at these different relative unities of hydration, the volumetric expansion is significantly lower to what a pure salt is. It's not perfect, it still starts to break apart bit by bit. However, for that, my proposed work is I'm going to use this calcium chloride and EV26 composite, and I'm going to use different salt loadings. I'm going to add binders and thermally conductive filler, and the goal will be to create a mechanically strong pellet with high energy density and high thermal conductivity. Of course, this will be to implement it into the packed bed reactor. And at the same time, I'm going to adjust my model to account for these changes. That's the end of question 3. Now for question 4, with the packed bed reactor, the question is, how do the multi-scale coupled heat and mass transfer phenomena of pelletized salt hydrates impact the performance of a packed bed reactor? So to answer this question, I'm going to first establish my model. This includes the governing equation of this packed bed reactor. I'm going to validate the model against literature and also my own experimental results. And I'm going to perform a parametric analysis to optimize the temperature lift and the thermal power output in this packed bed. So for modeling the packed bed reactor, I'm actually just modeling, in this case, the actual air in the packed bed reactor around the pellets. Whereas the pellets themselves, they're modeled, as I previously mentioned before, where they account for the diffusion and the reaction. But at the same time, I'm also going to model the air going around it. These are some of the assumptions. Again, transient 1D model, have the porous bed of dehydrated salt being hydrated, and assuming that the properties of the air in my bed are constant, independent of the temperature. Now I have my first governing equation, the conservation of energy. I have a transient term, I have an advective term, so this accounts for the flow of air through my packed bed. I have a conduction term, and I have that convection term. In the previous slides, I demonstrated convection to be a boundary condition of the pellets. In this case, it's going to be part of the overall governing equation as it unifies the pellets model with the packed bed model. And then and next I have my conservation of mass equation, very similar. I have my transient term, my advective term as the air flows through the packed bed. I have the diffusive term, and then the convective mass transfer term. Very similarly, the convective mass transfer was a boundary condition for the pellets. In this case, it's going to be part of the overall governing equation for the reactor. And then lastly, I also have to account for the momentum momentum conservation within the packed bed. So I'm using the Ergun equation that accounts both for laminar and turbulent conditions within the packed bed, and then Darcy's equation to calculate the velocity through the bed. Now I have here some preliminary results of my model. I'm modeling potassium carbonate, salt pellets, and then I have ambient temperature conditions and relative humidity. So this is what the hydration extent looks like in this packed bed reactor as a function of the length. As you can see at the introduction of my bed, you have a significantly higher increase of hydration rates, and this is due to the water vapor being introduced at this location. And then here we have the conversion of the overall bed. So this is how much of the bed has been overall hydrated through time. And as you can see, after about 12 hours, about 95% of the bed has been fully hydrated. And then here we have the temperature lift as the function of the bed length. And after about 10 minutes, that's how long it takes to increase the temperature. And this is, of course, due to the exothermic heat of the reaction. However, even though it takes about 12 hours to release about 95% of the heat, it takes about 3 hours for that temperature to start decreasing. And this is just due to the salt being exhausted. And of course, this provides us opportunities to optimize this bed where we could have that high temperature lift, the high thermal power outputs consistently throughout the use of hydrating my packed bed reactor. So for the proposed work, based off this, perform a parametric analysis to optimize this reactor design in order to offset about 4 hours of peak heating load in a building. And this model will be validated using literature and my own open system experiments. Here's my anticipated timeline for the rest duration of my PhD here. What I'm going to finish here in the fall. And then next semester, I'm going to try to finish up most of my experiments for the summer to write my dissertation and defend. Here are publications that have already been published. These are ones that are under revision right now, and these are 3 more that I have planned based on the work from my PhD. I'd like to thank my thesis committee for being here. Even though there's been some technical difficulties, thank you for staying so far. Also, of course, I'd like to thank my team, the Water Energy Research Lab. It's been great being with y'all. And then, of course, my family, my wife and my daughter, and expecting my next daughter in February. The many collaborators, including my army of undergraduate minions, and different people that have collaborated with me. And then, of course, my funding sources. This time I'll take any questions.